minimizes the objective function, which is written here, which I discussed. And so one way in the analysis of the equation is to minimize an objective function of x. And as I said, in the exact form, 3D bar without a temporal dimension, or more precisely, without an explicit dynamical model for the temporal dimension of the globe. This is good for operation with Now an approach, and that has already been described by Pavel this morning, so I won't go rapidly over that, can be easily extended, at least in principle, easily in principle, to the time dimension, to the case of an explicit dynamical evolution. So I suppose, for instance again, that we have considered time interval t0 between time 0 and time capital K, and that the available data consists of a background at time 0, x0b, lower indices in this equation will denote the time, will be time indices. So we assume at time 0, where the background, we have a background, essentially a forecast, which comes like this. Equal to the real x0, real state vector of 0, plus an error denoted zeta 0b with coordinate matrix p0b. And then we have observations, distributed in time 0, capital K, and at time k we have yk equal hk of xk, where xk is the real state of the time, hk is the observation operator for that time. It may vary with k, actually, even whether it varies or not, fundamentally irrelevant, but it is possible that at various times it is not the same quantity that we observe, meteorology or oceanography, plus an error epsilon k, and the covariance matrix of the error epsilon k is something which not properly written there. Okay, I say epsilon k, epsilon j. I should have written here delta kj, a chronicle, because I assume that all errors are uncorrelated in time. And for k and different from j, this should be zero. And I have a model which I assume for the time being that it is exact, that is the state, the real state of time k plus 1 is obtained from the real state of time k through an operation which I assume to be linear and represented by the matrix mk. So that's the real, what format I'm going to set. Now, what's the real evolution of this is the model, which is both linear and exact, which of course is an oversimplification with respect to reality. But again, we do theory in relatively simple situation and extend it more or less realistically to more complicated situation. And so that's the which Father described for me is a way to extend linear theory to non-linear situation. So the errors are assumed to be unbiased. That is, the expectation of all these errors is supposed to be 0, uncorrelated in time, and hk and nk, that is observation operator and the model operator, are linear. And then we define an objective function for that, extending the approach I described to the time-temporal dimension. And the same expression, which Fabian has already shown this morning. I have a term which measures the mass fit between x0 with also. I consider an initial, the model state, psi 0 at time 0. And I consider a solution of the model emanating from the psi 0. Xk plus 1 equals nkx psi k, oceanographic application. It can be 1 week or 2 weeks. And that observation, okay, and have a background x0b, and I take size 0, anything, I take 0, and I compute the corresponding model solution, which I write, I can represent symbolically or something. Like that. And I want to measure the misfit between that particular model solution and the background at x0 on the one hand and the observation on the other. So the term to measure the misfit between psi 0 and the background at x0, which is the same form as before, plus the summation over time of the misfit between yk, the observation at k, minus hk psi k, which is the another observation in the solution emanating from psi 0, weighted, again, by the covariance matrix of the observation error Rk, taken the inverse of the covariance matrix. And I can try to minimize this here as a function of psi 0. That is to find the initial condition psi 0 signal, which minimizes that objective function. It is of the same form as before. The only difference now being that I've introduced three solutions to model equation, assuming exact, so that the link, what can be called a kind of generalized observation operator, that is the link between my unknown, which in this setting is x is 0, and the observation, is rather complex in that it involves not only strictly observation, the physical process of observation, but also the process of carrying the model state from time 0 to time k. But except for that difference, which of course is a major difference when it comes to practical application, the conceptual background is the same as before. I just have an unknown, 0, and data which are related to that unknown for linear relationships, including the model, the linear relationship in this setting. So it is fundamentally of the same form as the objective function, which I told before. It is fundamentally of the same form with an hk and h will be much, much more complicated. But no, it's still of the same form. Is that clear? So I want to minimize that for respect to the initial condition, finding the initial condition, which minimize, which such that the model solution emanating that from initial condition minimizes, optimizes the fit, minimizes the mismatch, the misfit to the observation. So the problem is how to do this minimization. Actually, I mark something. Background may not be necessary if the observations are in a sufficient number and not as such they over-determine the problem, but it's essentially that two different initial conditions will lead to two different mistakes. Then they are not in the need for background. If observations are complete at any time, if at any time I observe a complete state of the system, which is not the case in meteorology, considerably, I don't necessarily need a background at all. In practice, that's all. And so, actually, nor is a strict linearity in the sense that, after all, if either the observation operator hk or the model operator mk is nonlinear, or both, I can still define an objective function of this type and try to define it, to minimize it. So, it's not forbidden, the confusion, it works. So even if non-linearity goes slightly beyond the relatively simple theory underlying the loop, from heuristic and critical point of view, we can try. And people have tried, and there is that it works. Okay, so now how to do such minimization? So what I'm going to say now for variance will actually have to do with minimization, and no more particularly with meteorology or any specific physical application. What I'm going to say now has just to do with minimization on a large computer. So I call the initial condition U, and U will be used as for this what I call the control variable of the problem. Control variable says very well what it means. It is the quantity I'm going to vary in order to obtain the best fitting observation, the minimization of the objective function. So I'm going to vary the control variable psi 0, which now intent U, forget what its physical meaning is, in order to optimize something. So I can do that. I have U as dimension 10 to the 5th, 10 to the 6th, 10 to the 7th, and a very gigantic dimension. I want to minimize a function in a very large dimension. What could I do? I could possibly explore the space of initial conditions by computing the objective function in many points and trying to find where that's easy in dimension 1 or 2. Or small dimension, larger dimension of your state will become very costly. There are methods which are for doing that. For instance, by something which is called simulated annealing. Simulated annealing is a kind of ensemble method in which I don't know which well. I basically know how it. What is done is that you take the ensemble space, you take many points, find out, and then you give a random motion to this point, random perturbation, and at the same time you define the objective function. You start with flat objective function, and little by little, the idea is to increase and to give more and more variation to it, and to add something to that particles of random motion, and at the same time are submitted to a force of gravity and go down along the values of the objective function. It's like you have a large number of particles on a table, and then I constantly hit the tables to produce random motion, and little by little I change the shape of the table, and it has bumps and holes. And it is easy to understand that at the end of the process, if I can tune both the random motion and the way I change the shape of a table, all particles, or most of them, will be concentrated in the deepest hole. So that's essentially, in rough words, from what I understood, what simulated annealing is. But it works efficiently only in a relatively small dimension. So I don't think that for our problems it can be useful. Maybe someday there will be a method of stuff. Now there are things which are very well known, which are gradient methods in general sense. Gradient methods are simple. Can you see what I write here? Well, I do have this function J, and I do a cross section in 2 dimensions. Of course, in reality, it is dimension 10 to the 6 and 10 to the 7. So this is the minimum of the objective function. And these are the isodines, isosurfaces of J. J is constant along the edge of the surface. So at a given point, I can take the vector with components dj, the partial derivative of dj with respect to dui. Now, from now on, my control variable, this is a vector with n components, or n in the dimension of u. And of course, it is directed along increasing j, and it's perpendicular to the isosurface perpendicular in the sense of a scalar product, which is simply defined by, Euclidean product, Euclidean scalar product, sigma, the ui, di. And if I have that, I can take the direction of the gradient and go down the gradient until I reach a point, which is about the place where J is minimum. That will be the point with the line emanating along the gradient is tangent to an iso J. There I compute a new gradient and go there, and it can be seen, but actually, if the minimum this will converge, if I do that systematically, it can be shown mathematically that this will converge to a minimum. And if there is only one minimum, it will converge to that unique minimum. Doing that like I've just described here, just taking the direction of the gradient, first of all, requires being able to determine the gradient, which is the crux of the problem. But actually, the simple method, which is called direct gradient method, turns out numerically to be very inefficient. Because in most situations, with iso J line, the original coordinates used to be, will be actually in some direction very elongated. Which means that the gradient will be like that. And then your gradient like that, and gradient like that. And that's very inefficient for reaching the minimum. So direct gradient is, as a general rule, if you're interested by this kind of thing, you can retain that direct gradient. Just going down to the local gradient is very inefficient. So there are more efficient methods which all make use of a successive gradients which have been computed in order to determine more accurately the direction of a minimum. Actually, what we want is to point to the direction of a minimum, not to point to the direction, not to move in the direction of gradient. So if we have a number of gradients, which have been computed several times, at several steps, we may be more capable to point to the minimum. And so there are several such methods that you read the whole field of applied mathematics, optimization. I mentioned two. One is the conjugate gradient algorithm, which gradient algorithm, which actually works very efficiently in case the objective function to be minimized is exactly quadratic. And as I've written it here, h, okay, and the model are linear, this objective function is exactly quadratic. So the shape, this something like this, these isolines are exact ellipses. They are curved here, in large dimension, they are ellipses. So the conjugate gradient algorithm, well, is based on the notion of conjugate direction in quadratic forms. Conjugate direction, this direction is conjugate with that direction. They are orthogonal for the scalar product defined by the matrix of the which underlies the quadratic form. And so it's used on exploiting exploiting the property of quadratic forms, and in particular, a conjugate algorithm can be shown to converge exactly to the minimum in at most n iterations of a process, where n is the dimension of the control variable. Although in our case, it was many iterations. Another possible method is called Newton method. Well, the first is in our younger age, the Newton methods for finding the place where the function is equal to 0 by taking the derivative along the direction and going there, and taking again the derivative and so on, which is one very efficient method. Well, minimizing the objective function is the same way of finding the place the location at which the gradient becomes 0. And so the Newton method could be used to find in the point in slip space where the gradient is 0. Now the gradient is a vector, and so since in Newton methods you have to take the local derivative, you have to take the local derivative of the gradient, that is the metric of second derivatives. We don't know it. But then there are methods which are capable of building successively from the gradients which have been computed an approximate matrix of second derivative. The matrix of second derivative are usually called Hessian. I'm sure some of you, and not all of you, know this expression. Hessian is the matrix of second derivatives. You have a function J of u, and the Hessian is the matrix whose entries are all the second derivative dj, where dui, dj, where I and j will run over all the components of j, which is the vector. Okay, so no inversion will be a system which progressively computes an approximate Hessian, and the inverse Hessian. And there are quasi inside the method which don't exactly compute an exact Hessian, but will progressively build an approximate Hessian from the successive gradients that are computed. And this can be done, and this argues together with the conjugate of algorithms in our problem. Now, all that does observe a question. One question, which is how to have a local gradient in the first place. I'm in some place in state space, and I want to know which direction I will have to go closer to the minimum. One way, of course, could be to do some kind of random walk. I chose a random direction. I move either random direction. I go one way in random direction, one sense. If the function or objective function increases, I go down. If it decreases, okay, I go some distance down, and so on. In large dimension, this is totally inefficient. So I have to find the gradient. That is, the vector whose components are the partial derivative dg ui. And I remind you that starting from u, computing g, requires integrating the model over the whole period 0t. It's not a minor computation. So one way to compute the gradient would be simply to compute it by finding differences. I'm at a given point u, the space, control space. From now on, I will call it control space. I am at some point u in control space. And I want to compute the gradient. So I perturb one by one all the components. u1, which I send to u1 plus delta u1. And I compute j for the perturbed state, well, u plus delta 1. You will understand what I mean. This means that I perturb only component 1 minus j of u times delta u1 divided by delta u1. And this, of course, is an approximation of partial derivative dg over du1. And do that for all n component intervals. And I obtain an approximate gradient, finding different gradient. But this requires as many computations of the objective functions as there are dimensions in the system. 10 to the 5 or 10 to the 6 integrations of the model. Forget it. Actually, around in 1992, there was a man whose name is Ross Hoffman, in this of you, who is working in a company in Cambridge, Massachusetts. But it did variational assimilation for this process with a model with a dimension of a few hundred. And he did that. He perfectly realized, was perfectly aware that the numerical approach he was using would not be implementable in a real situation. But still, he found it interesting to try to see what the results were. Because as long as the results were concerned, doing that was, was correct. And it was a way to check what potentially could be obtained by variational assimilation, although he knew very well that the numerical method he used couldn't be used in a real practical situation. But he obtained results which were significantly useful and which showed that actually that method produced results which from physical point of view were reasonable. So what I am going to describe now is a method for computing gradients, which is the direct perturbation. That's what I explained. That requires many explicit computations of the objective function J as they are competent in U. It's possible, practically, not theoretically possible. And I'm going to describe the adjoint approach, which is a way to computing gradients at a numerical cost, which, first of all, contrary to the direct perturbation, is not proportional to the number of the dimension of the control variable, and whose cost is numerically a few times, few being 2, 3, 4, the cost of one direct integral computation of the objective function. And that's the adjoint approach, Who is familiar with adjoint approach? Yesterday, Quan Lee, I don't know where he is, presented application of the adjoint approach to the dynamical problem. Who is familiar with the adjoint approach? No one. Okay, that's the course is naturally. Who has heard of it has vague knowledge of it? Vague knowledge. And who has never heard of the adjoint approach? Okay, so I'm going to describe it in some detail. So, the adjoint approach is a very efficient way. It is. It has theoretical interest for mathematicians and himself, that I won't speak about. It is a very efficient numerical way of computing gradients, to be computing exact gradients, not approximate gradients like finding exact gradients, to the accuracy of the computer. And it can be used to many problems, obviously minimization, but also sensitivity studies, and not generally control. And tomorrow I'll show you a simple example, not so simple, but an example in which clearly how the adjoint approach can be useful for what is called a control problem. Control problem is generally all problems in which you want to act on a system for the way to act in order to take the system in the states you know. It's very important when you cannot act on the system just as you want. And control can be purely numerical, it can be physical. You want actually to act on a physical system to take it in the situation you want. Eating, exerting pressure, exerting 4 million. Okay. So I have an input vector, U with component Ui, dimension n. And I have a numerical process, which is implemented on the computer, code, which starting from U, produces from an input U, produces an output V. V is the output vector with component Vj with dimension n. And no relation between n and n. No necessary relation. N can be larger and smaller than n. That's not the problem. V is the output. For instance, the process can be the integration of a numerical model. U is the initial condition, and V can be the prediction what the model produces at a later time, in which case n will be equal to n. But V can be also, depending on the context, the sequence of states, for what we'll use it in the substitution, the sequence of states produced by the model over a given period. Starting from a given initial condition at time 0, V can be the sequence of states produced by the model between time 0 and time k. And this is what I will illustrate. In that case, n is n times the number of time steps at which I look and the output and the output and so on. And so, v is the function of u for some function, which I call capital G, a complicated function, but it is implementable. I can do the computation. And given u, I can compute v. Run the model. And now I consider a perturbation delta u on the input. And I look at the resulting first order perturbation and the output v. And from elementary differentiation, I know that the perturbation of the component vj of the output, yes, I will systematically use the index I for the input and the index j for the output. The first order perturbation dvj on the j component of output is equal to the summation over I of the partial derivative dvj over di times the perturbation delta ui of component ui. Plus, of course, exact perturbation contains in higher order terms in delta u. I consider only the first order. And this can be written in the vector matrix form as the perturbation, first order perturbation delta v being equal to the initial perturbation delta u, the first order output perturbation delta v, as being equal to the input perturbation delta u, times the matrix of participation as the partial derivative of the vj with respect to the vi. The matrix of all partial derivatives. It exists as a mathematical object. I don't mean that it will be very easy to compute it explicitly, but as a mathematical object it exists. And this matrix has a name in mathematics. It's called the Jacobian matrix, after the name of the German mathematician Jacobi. And so, delta u in vector form, the first order perturbation in the output is equal to the perturbation in the input multiplied by the Jacobian of the process G, which is repeated here. And then I consider a scalar function of output. I take the output and then on that I compute scalar quantity. For instance, the misfit between the sequence of states produced by the model and the observations. So, since v is a function of u, this quantity is a combined function of u. Prove it. And I want to relate directly the variations of u with the variation of j as the output. So I want to skip, in a sense, the dependence on v. I want to go directly from the variation of u to the variation of the scalar output j. This is exactly what I want to do in the problem. I want to relate the variation of the misfit function j to variation of the input control variable u. This is exactly. So I consider the gradient of j with respect to input u. And a strict mathematician here, maybe you cannot write that. This is not the same function. This here, gradient of j with respect to u, is the composition of j with j. So you should write a new function, k, equal the composition of these two things, and you should speak of a gradient of k, or the combined function, with respect to u, not the gradient of j. Okay, right? That's it. I still use the same. And I use the general differentiation, which tells me that the partial derivative of j, okay, with respect to the input variable ui, is equal to the summation of all j of the partial derivative of j with respect to dvj times the partial derivative dvj over dr. And here I have the gradient of j with respect to output, and here I have again the components of the Jacobian matrix. But here the summation is done with respect to the index on the numerator, dvj, while on the previous case, the summation was done on the index I, which is at the denominator. So it's again the vector matrix multiplication But then the multiplication is not by the Jacobian matrix, it is by transpose. And so I have a relationship that I go from a gradient of J with respect to the output to the gradient of J with respect to the input by multiplying that gradient with respect to the output by the transpose of the Jacobian matrix. So I can compare these two formulas of the formula. This, the direct Jacobian matrix, defines the relationship from the input of from the perturbation of the input to first order perturbation of the output. And this formula goes from the gradient with respect to the output to the gradient with respect to the input. To leave the C, but if N and M have different dimensions, this matrix is defined as N rows and N columns, and this one as N rows and N columns, as must be, because here we go from a vector with N components to a vector with N components. This is the first case. Well, since this is a transpose matrix, the numerical cost of this multiplication must be fundamentally the same as the numerical cost of this multiplication. And this essentially amounts to running the model twice. One with no perturbation, and one with a perturbation, or maybe something like that. I mean, this is not, for a given perturbation delta U, this is not very costly. The cost of the sequence should be the same, or approximately the same. So this gives you a way, must give a way to compute this gradient with respect to the input at a cost which is similar to that cost. So that may not be absolutely obvious, but I mean, what may be absolutely obvious is what this implies in practice. But I think argument is convincing that by appropriately using this equation, I may be able to compute these gradients at a relatively low cost. So before I go to more detail, and I come back to that tomorrow, I give some other information. Let us suppose that G, the whole thing, the whole process, is a composition of a number of successive steps. For instance, successive time steps of integration of a model. So starting from the input, I do one time step, and then the second one, you see I put capital N. If I was consistent, I should have put capital T. I'm sorry, it's a slight inconsistency between the notation as is here and the notation I used on the previous slide. That's right. I take, so this is a composition. This is the symbol, the standard symbol of mathematics for composition of operations. But if now I take the Jacobian of that, the matrix of partial derivatives, then the chain rule again for differentiation of the composition of operations tells me that the Jacobian of the whole thing is the product, in the sense of a numerical product, of the corresponding Jacobians. This is a multiplication of matrices in the ordinary sense, a real multiplication, not a composition. And so the Jacobian of the whole thing is the numerical product of the Jacobians. And what I must take is the transpose of that. And it is known that the transpose of a product of the matrices is the product of the transposes taken in reverse order. So the G prime transpose, which I need in order to compute my gradient, will be obtained by first multiplying the gradient of J with respect to the output by the Jacobian transpose of the nth operation times the Jacobian transpose, the transpose Jacobian of the n minus first operation, and ending by the Jacobian transpose, the transpose Jacobian of the first time step. And each of these time steps is decomposed into more elementary operation, down to the elementary arithmetic operation. So the whole thing, in reality, in linear application, is only a sequence of arithmetic operation. Maybe a long sequence, but a finite sequence of arithmetic operation. So the adjoint computation, the transpose computation of this space, will be a finite computation of a finite number of transpose operations, whatever they are. Let's be clear for what they are saying here. This is what I'm going to obtain. And of course, it shows that the transpose, and I say adjoint because the notion of an adjoint operator in mathematics is only a generalization of a notion of a transpose operator, or a transpose matrix, must proceed backwards in reverse order of direct computation. So actually, this is absolutely obvious from this. I go from the gradient to respect to the output, to the gradient to the respect to the input. Obviously, I proceed backwards with respect to the basic computation. Now there is one thing. Yes. If J is nonlinear, then the local Jacobian G prime depends on the local value of the input U. Derivative of a nonlinear function depends on the local value of the variable. A linear function that doesn't depend on the local value of the variable, definition of linearity. So this, the value, local value in case G is nonlinear, G prime depends on values, quantities, which are produced by the integration. And when I use G prime, these values must be available. So either I must keep them in memory from the direct integration, or I must recompute them in the course of the adjoint computation. And of course, this memory requirement is the price to be paid for the gain in number of operations. As for the gain in operation, it can be shown that if everything is kept in memory, and if all that sequence is only a finite sequence of arithmetic operations, then the total cost of an adjoint computation, the total cost of multiplying a vector by G prime transpose, is at most 4 times the total cost, I mean here, number of arithmetic operations, the number of arithmetic operations of a direct computation. In practice, it is about 2. So I can do the adjoint computation at basically the numerical cost of 2 direct integrations of the one, which means that I can compute one gradient at the cost of integrating once the model over the assimilation period, keeping in memory all quantities are computed in the meantime, of course, then integrating backwards the preference backward the adjoint computation, using the value that is kept in memory in the direct integration, and the cost of the backward integration will be basically twice the cost of the direct integration. So I'm going to describe in more detail what that means in practice, but are there questions at this stage? Yes?
Let's go back to slide 6.
To slide
6.
2.
6.
6.
Just a very nice question.
This one?
Yes. So you're talking about the number of divisions. I'm just wondering, is there any optimal number of observations regarding to the resolution?
Oh!
You said the background is not necessary.
Yes,
The resolution is sufficiently large enough.
Yes.
To have the optimal number of observations.
Well, I mean, given the background,
Without background.
well, the number of observations must, of course, be at least, if you want to over-determine problem, or over-determine the problem, the number of observations must at least, distributed in time, but at least be equal to the number n of parameters to be determined. As I mentioned, if you want to determine n initial parameters, we must have at least n observations.
Yes, but suppose I have two end observations.
Yes.
Then I have more than enough observations, basically.
Well,
So
it depends. It depends if these observations bear an independent quantity. If all observations bear the same quantity, it wouldn't be enough. So it depends on how the information contained in the observation is related to the initial condition. And that's a very difficult problem, and I am totally unable to give a general response as to that.
okay.
I said that as a remark, but I don't mean it is practical, that remark as in a practical importance for meteorology. In any case, there is always a background. And from the time there is a background, the problem is overdetermined, because for each parameter to be estimated, there is already one explicit estimate, which precisely is the background. So the problem is, from the time there is a background, the problem is obviously overdetermined in the first place. Yes, Pavel, you have a question then?
So in practice, our model of quantum mechanics.
Yes.
So they have lots of if-then conditions.
Yes.
So they're not smooth.
Okay.
Doesn't this mean that there's an internal sort of weakness in this one approach?
Okay. So I have an if condition. So this is the sequence of operation, a flow chart of code. And then sometimes there is an if statement. And depending on if, I go this direction or that direction. Then may rejoin on evenness. Okay. So I first do a direct integration. Then I go with the direction. When I do the reverse adjoint integration, I have to remember which way I want to go. And to go flip the adjoint integration on this way. And if I don't run on that way, I need to go that way. I have two paths, two possibilities, and I may do the indirect integration following the same possibility, the same path I took in direct integration, just in the reverse order. So I must keep in memory, or be able to find afterwards, which one I will do. As long as I'm not exactly on the if, on the critical value of the if statement. That's totally transparent. You know, at the condition if of x larger than 0. I can do something and do something. If x is strictly positive, I go here. If less is strictly negative, I go here. And I have a local gradient. Just like if I have a function which has an angular point, the local derivative is defined everywhere on either point on either side of the local polygon.
If you iterate, and your x changes what? So
Okay, so I iterate, and the gradient tells me here I could go this direction and the direction, and constantly there may be difficulties. Actually, specialists of optimization have dealt with this, and they have produced minimization codes which are able to deal with this kind of application. Of course, at some additional cost, no, like they have produced. For what I know, meteorological applications, no one so far has encountered a real problem, real problem, this kind of processes. That's what I'm saying. Some people have a priori smoothed the angular points in order to avoid difficulty. But I stress that the real problem, if there is any, is not strictly in the presence of angular points. It is in the fact that the gradient may vary very rapidly from a very small change of the initial condition. If it is true that if the gradient changes very rapidly for a very small change of the initial condition, then we are in an unfavorable situation. But it is the question of whether there is strictly an angular point or not. But so far, some people have a priori, without even checking the whole thing, because even doing the check would have been considered too costly, smoothed out some discontinuities, which Actually, in some cases, it's reasonable. I mean, you have humidity in the atmosphere, and humidity can saturate, and then precipitation will start. Over a mesh of the model, there is not a state of no precipitation, and then a state of precipitation over mesh, but that doesn't exist typically. There will be a intermediate state in which there is some local precipitation, some very small amount of precipitation over the mesh, which correspond actually to a smooth transition between no precipitation at all and precipitation everywhere over the mesh. So actually, in physical reality, in many situations, it is reasonable to smooth the transition instead of doing for every grid point. Is the humidity saturating or is it not? It may be saturating in a small part, in a small area of the mesh. So it's reasonable. Actually, we had an example. It was not for the terrestrial atmosphere. It was for the atmosphere of Mars. We developed a model of the atmosphere of Mars. It works very well. And on Mars, you may know that the atmosphere of Mars consists essentially of carbon dioxide, and that is carbon dioxide condensates to the ground, creating polar caps, which for a long time were interpreted by people using telescopes to observe mass of caps made of water ice, not made of CO2 ice. And so that changes when CO2 condensates on the ground, but of course changes the albedo of the ground, and that is strong impact on the radiative balance of the atmosphere. And we have put a kind of all or nothing CO2 ice at every good point. And you obtain crazy things, and then we smooth the thing by saying not all CO2 condensates at once over the whole mesh. It condensates first to a small amount, so we consider that full condensation, we actually artificially introduce the depth of the CO2, and which smoothed out the thing, and gave much more reasonable results. So in many cases, it will be reasonable to smooth out the if-state matter. And yes, and right, to such things, I don't know of any example, I don't know how it been, but I don't know of any example in which if statements in the meteorological model have created a problem for minimization. With the student combined, we did experiments at the time to check this point. We kept the if statement as it was, and we just did the minimization, ignoring there was any if statement, but still going this well. That way, even if underfound, but efficiency of the minimization was simply not affected by the, maybe very slightly affected, but there was no. In the case we consider, there was no significant impact of the if statement on the global efficiency of the minimization. As if, you know, for the whole objective function as the function of the initial conditions, the if statements created, you know, maybe an angular point, but an angular point with a very small angle. So that in practice, maybe someday there will be a problem with that. I mean, but it's absolutely fully safe. Okay, are there questions? Okay, so that's the principle of the adjoint method, and so I go directly. I go directly to what it means in the practice of variational assimilation. Enough for this time. But tomorrow I'll come back and be more detailed. So again, this is the non-linear case. And for that, I go to the linear case. So this objective function, the same as before, with linear observation operator and linear control variable psi 0 equal to. So first thing to do, so part again the linear case. First thing to do, you integrate for given psi 0, you integrate the model by this computation, and then compute the message function. Actually, well, no, compute it's not strictly necessary. Then you introduce a variable denoted lambda here, which have the same dimension as the state variable x of psi, same dimension. And you define at final time lambda k, equal hk psi k minus yk, that is the misfit between the model solution and the observation at the final time, time rk minus 1 time hk transpose. The hk transpose is very comes from here. Now you go one step backwards in time. I should have put dots here. To stress that they are supposed. You proceed backwards in time. And at each backward step, you take lambda k equal lambda k plus 1, because we go backward in time, time nk transpose, the transpose of the model, plus a term, which is of the same form of this one, which is directly proportional to the misfit between the model solution, the current model solution, and the observation at time k. Time multiplied by rk minus 1 multiplied by hk transpose. And you get like that to time 0, which you obtain from time lambda negative 1 for the same process. And then you have an additional term at time 0, which comes from this term, because this term depends on psi 0. So an additional term, which is the misfit between psi 0 and the 1 and time b, at the 1 and time 0, multiplied by p0 minus 1. And you prove, show, that what your lambda 0 you obtain is precisely the gradient of the objective function, defined like that, with respect to the initial condition at time 0. So this involves first a direct integration of the model, and you must do it, because here you must introduce explicitly the misfit between the current solution and the observation. So you must know psi k. So you must have done this direct integration to begin. And once you've done it, you integrate backwards what is called the adjoint equation, which starting from lambda at final time and obtaining at lambda 0 precisely the gradient of j with respect to the initial condition. So it means that the result of the interpretation of psi k must be kept in memory from the direct integration. Now let's go to the nonlinear model. After all, the procedure I've described here is valid for any process, as long as it consists of operations which are differentiable. But if it is only locally, then it is only a number of discrete points, but it is not differentiable. As I told you, no problem arises. The problem has arisen so far.
You just said that psi k should be kept in memory.
Yes. So
that is page of.
What did you say?
It's page of psi k.
Yes. Strictly speaking, you're right. Strictly speaking, it is only hk of. So that if there are only a small number of observations at a given time, it is three. Now let's see for the nonlinear case. So now I suppose that I do that forbidden on the nonlinear situation. Even though there is no very strong theory to support what I say, I can still try to minimize this function with hk being a nonlinear observation operator, typically the radiative transfer of the operator or radiative transfer function I was speaking this morning, and nk being a nonlinear model. And basically, there is an adjoint integration with it the same as before, except whenever, can you see it well? It's being written in green here. Can you see it? Can you see it well? Do you see them in the back? Yes, you can see that. If you compare this equation with the equation, the one before, the only change is that when there was a transpose operator here. Now I have the transpose of the corresponding Jacobian. course, a nonlinear operator doesn't have a transpose. Well, of course, a nonlinear operator doesn't have a transpose. Only a linear operator has. So you must declare the local Jacobian of the model or the observation operator, and the observation operator is nonlinear. And this is where, actually, the basis solution will also come in. Then you will need more than just HP or HP. And when there is, in the adjoint integration, there was an observation operator acting on the state, then it is here now, the full misfit, but still non-linear operator, acting, you take the same misfit. And this gives you the gradient, and the exact gradient. This is not an approximation. This is not an approximation. It gives you numerically, to the accuracy of the computer, the gradient of the objective function with respect to the initial condition. And you can feed this gradient into a descendant horizon, and little by little converge to the minimizing solution. And then example, yes?
You have the PB matrix there, yeah?
Yes.
Inverted.
Yes.
And you want to avoid that. Or
Well,
the whole problem.
it is there in the objective function to start with. So it is true. Actually, okay. You can define PB by its inverse in the first place. It's not impossible. I don't think that actually is that. But PB is defined in such a way, but it will be easy to compute it inverse. But actually, those schemes could be very well developed by defining the PB matrix by its inverse in the first place. Anyway, no, that's you're right. But in practice, this is solvable, and PB is written in such a way that it is relatively easy not to compute PB inverse, but to make the product of inverse PB times the vector. This is what appears here. The inverse PB times the vector. And of course, are written in such a way, the structure of PB is defined in such a way, and comes as written in such a way. This is relatively easy. And again, this is not an approximation, and I was saying, but in practice, it works. It was shown by people in the 80s, but it works, which was not at all obvious to start with. And it gives results which are physically reasonable at the cost of a number of iterations, which is a few tens. Something like between 30, 50, 60 iterations. Even in dimension as large as 10 to the 6, or 10 to the 5, or 10 to the 6, or 10 to the 7. Which I will say, in a sense, is surprise. You obtain results which are physically useful at a relatively very small number of iterations if you consider the numerical dimension of the control space. And it is used operationally for operational weather forecast every day at a number of places. It is ECMWF, which started in 1997, which is already almost 14 years ago. Then a number of other meteorological services, Météo France, the French meteorological services. Actually, Météo France and ECMWF worked very closely on this occasion. It is mostly people from Météo France who did the work, at ECMWF. The British Meteorological Office, the Canadian Meteorological Centre, which also has an ensemble feeder, which is costly, but which allows them to make clean comparison between the two approaches, which is very useful. The Japan Meteorological Agency and many others. Okay, so that's all for now. Thank you. Okay, tomorrow I give you results which have been obtained by operation of assimilation, and I will some more about the adjoint equation and take the case of a simple partial differential equation, the equation of heat diffusion, d of temperature of the T equals k diffusion coefficient times the Laplacian spatial Laplacian of temperature, and show what it does. It's an interesting example because the differential equation defines a well-posed problem for integration into the future. So one might ask, and what about this reverse adjoint integration? How does it work when the the basic problem leads to a well-defined integration only for integration to the future. Well, I'll show you perfectly can be seen mathematical ways, but if the direct problem leads to a well-posed problem only for evolution into the future, the corresponding adjoint problem is well-posed only for integration into the past. And they are both mathematical and good physical reasons for that, which I'll explain. Okay.
Yeah, then we have a half an hour break.
Yes.
Yes.